over. Jane, here's the clicky. Our next speaker is Professor Jane Greaves. She is at the University of Cardiff in Wales, which is a lovely place. And she's going to talk about all sorts of interesting gases that you can see with radio telescopy and focus on Venus. And she's also an navigational artist, as am I. And so she has maybe a surprise for us. So take it away,
if
Jane.
we have time at the end. Okay, just need the slide up the front, please. Okay, my job to do this. Got it. Finally. Okay, so we're moving on to Venus and some of my team's new observations today, and the exciting possibility we're looking at some molecules that relate to life that is there today, microscopic-sized life in the clouds. Okay, we've heard wonderful things about spacecraft. I love spacecraft. But I trained as essentially a radio astronomer. I work at wavelengths of a millimeter up to a few centimeters. So why would you want to use these? Well, I think this diagram shows very nicely. It's a theoretical calculation of the habitat size on several bodies of the solar system. And you can see there's a lot of these. And so you can't necessarily urgently send a spacecraft to each of these, as we just heard for Enceladus. So sometimes I think what motivates us is urgency. I just want the answer now, right? Like now. Also, we might have a new idea. We might think of a completely different body. We might decide there are fire-breathing dragons on Io. We want to turn a telescope on that and find your dragons, okay? And our telescopes on Earth are very adaptable. So maybe you think of a biosignature that involves something that changes very fast, or that's polarized, or that's some kind of wavelengths you never normally think about. We have telescopes to do that. I just wanted to show you some of my favorite, most beautiful telescopes. So this is the ALMA network of telescopes on a very high plateau in Chile. Let me see if I can do the pointer. To give you an idea of scale, here are some regular-sized trucks. Here's one of the two giant transporters on which they physically move the telescopes around to reconfigure for different kinds of observations. You've seen this already this morning. This is the wonderful 100-meter diameter Green Bank telescope in West Virginia, apparently one of the world's largest moving structures that humanity has ever made. And here's one of my favorites. This is the 30-meter diameter IRAM telescope in the south of Spain. And that's what we used for one of our first astrobiological projects. Okay. So this is Enceladus, but the data we got is the spectrum you're looking at there. You're going to see quite a lot of these in the talk. So what you're looking at, if you're not familiar, you're going from short wavelengths to long wavelengths as you go left to right. This kind of stuff here, this is just random noise. What you're looking for is either an emission line going up or an absorption line going down at a very, very specific wavelength. We have very high precision in that. We're talking about like, a part in a million or something. And molecules undergo quantum transitions between different states at these very precisely defined wavelengths. So we could look and say, we want to look for methanol, which is what we did. So these methanogens can not only make methane, they can also make methanol, the carbon molecule shown there. And so we found some. You can see it in the spectrum. And this is a case study of how to be careful with your astrobiology. So we looked at it and we decided there's no way this is a biosignature. Firstly, the scale of it shown by the blue cloud in the artist's impression, it's much bigger than the moon. And then we found there's more methanol in there than, in relative abundance to everything else, than Cassini sniffed out, actually at the vents. So that doesn't work. The life forms are not outside the moon. So what we're seeing is some really weird chemistry in Saturn's plasma environment. Also, we realized Enceladus, like the man said, is really small. It's too small. So we thought we'd go to our neighbor planet next door. This was a few years later. And this was based on the 1960s idea that as the surface of Venus appears to have turned into some sort of scorching hell, owing to a runaway greenhouse effect, making it much too hot for any biological functions, that pre-existing life of a microscopic nature could have adapted to float in the high clouds instead of being on the surface. So the clouds are pretty hostile. They're very acidic. But this isn't a completely crazy idea because planet Earth has a limited aerial biosphere. It's relatively very small compared to the abundance of life elsewhere on Earth, but these micron-sized creatures do float up there. And it's an open question if it's a very active environment or they're just kind of there and a bit more dormant. But, you know, it's a possibility. I should also stress that we don't know if conditions on early Venus were ever right for life to get started. So if we think of Earth and Venus as two similar planets made by smashing the rocks together till you've got one very hot rock, path to the Earth in the lower right went fine, but Venus must have taken some different path, and we don't know quite where it turned off. So if there were early oceans, life might have had a few hundreds of millions of years, or even a little bit longer, to get going. Could have been oceans and land masses. On the other hand, if the water was kind of never really built in or was lost very, very early, there could never have been enough water for life to develop. But it's still worth us taking a look. What my team is trying to do is what exoplanet astronomers would call a gold standard search. So finding two gases that could plausibly be biosignatures. So something that has some biological function. Okay, and you ideally don't want your biosignature gas to be made easily by something else, so not by volcanoes or sunlight changing the molecules in the atmosphere. So if you're an extraterrestrial scientist at this equivalent conference somewhere out there in the universe, you're saying methane and oxygen, these are great, I'm going to look for those on this Earth planet we've just discovered. And they would be products of living things because they disappear quickly if life stops making them. So Venus has the advantage over doing extraterrestrial studies that it's really close, it's our neighbor planet. And so we can look for gases at very, very small relative abundances. And so we can look for ones that are very distinct. As we heard, phosphine, pH3, is very distinct of life, and so in fact is ammonia, NH3. What we're looking for is a classic out of equilibrium situation. So life is an out of equilibrium process. And a redox disequilibrium is when you have molecules dominated by oxygen, such as the sulfuric acid. You see the formula there, it's mostly oxygen atoms, and we know that's there. Also there with reduced gases, which are mainly dominated by hydrogen, and that balance doesn't stay unless something is making it. So we set out to look for phosphine. We're very privileged to have used the telescope on the sacred mountain, Mauna Kea, on the island of Hawaii. And it's currently the East Asia Observatory operating this James Clerk Maxwell telescope that you see in the picture. Well, you actually see the shadow of it behind its protective wind blind. Okay. And we got a spectrum after about 5 hours of telescope time. And there was something there which was like the most shocking moment of my life. The white spectrum you're looking there, you can see there's a dip in the middle at the right wavelength. And that was crude, but we went, and they very kindly gave us time on the ALMA telescope network. That's actually a preliminary version, but the orange spectrum confirmed that in the same place. And so we had phosphine. Wow. So that was controversial, remains controversial, fine. I have to say now I'm like, this is routine. We look, there's phosphine again. So I'm showing you a time series of the spectra we've got over our various observing campaigns. Our really deep one is the 2022 one. The red curve is a model of the atmosphere that fits that. You can see that dip is there really nicely. And I've overlaid the red curve again on the other spectra. So you can see there's maybe a little bit of variation, but it's kind of there in all of them. Okay. Important to confirm, this is even more controversial. This spectrum was taken at a 4 times higher frequency with the Sophia Airborne Telescope, done by an independent team led by Martin Cordiner. We disagree in very subtle ways on the processing of those difficult data, but you can at least process the data in a straightforward way, as I've done here, to find another of these absorption lines in the right place. Okay. Sad we don't have Sophia to try that again. And then finally, on phosphine, something I'm very proud of, we went back to the James Clerk Maxwell telescope and we managed to make use of a larger bandwidth. The significance of this is the molecules collide with each other and allow the absorption to happen at a slightly wider range of wavelengths. If they collide more, if you're at a denser, lower down, warmer part of the atmosphere, your line gets fatter. And this is what we've been able to do, and we've got this beautiful orange spectrum here. The model is fine. The model fits beautifully with no particular fancy work done. It should be nothing here. The narrow bit means high above the clouds. It should be destroyed by sunlight, and there's no line. Fine. Also, you hear, 5 sigma is a really robust standard to go for, 5 times above the noise if you are aiming to announce something exciting. When I worked out the area inside the orange spectrum, it's 50 sigma, so I'm like, okay, guys, that's enough. So moving on to ammonia, so I don't take up too much of your time before coffee. The phosphine search was really my mad idea, having read some random piece of science. Ammonia was much better motivated. So in particular, my colleague at Cardiff, William Baines, in conjunction with Paul Rimmer at Cambridge University, came up with this idea that maybe the clouds don't have to be super, super acidic. If there is production of ammonia gas, it can neutralize some of that acidity. And that actually helps explain some other observations, one of which is that the droplets don't appear to be purely liquid. They might be more like a kind of slurry or sludge. But if life was making this ammonia, that could be it saving itself, essentially from corrosion. So it's kind of maintaining its own habitat. So this is the speculation in Williams' paper. And then I remembered, you can take spectra of ammonia because it absorbs strongly at a wavelength of about 1.3 centimeters. So the Green Bank Telescope people very kindly gave us time to try this. I think these are literally the first ever spectra taken at centimeter wavelengths of Venus. I couldn't find any others. So like, this is great. Okay, this is what we got. So the light blue one, we didn't really see anything. This is really difficult because it's never been done before. We got a rather scrappy spectrum in February 2022 when the telescope beam was very much on the night side of Venus, and there's not kind of anything there. But they kindly let us do it again and do a wider band in October last year, and this time the spectrum actually really does have a shape. I've done a very approximate model. There are no radio spectra. There's no code to model it. And it looks like you can fit it very nicely with that red dashed line. And that looks like I drew some random squiggle, but that's not the case. That's actually a composite of approximately 10 different quantum transitions of ammonia that blend together. So I don't think it's random that the model fits the shape there. And that allows us to deduce we've got a few parts per million. This is really low abundance at these particular altitudes, and that's given to you by how wide these features are. So we're frustratingly not quite there. We're hoping to go back to Green Bank and get the instrument to go a bit wider, fatter lines. What we've got is what's sketched there. We're seeing both molecules, but just above the temperate zone. So what I'm hopeful for is that the actual source is in the temperate zone, and we're seeing a fraction of the molecules that drift upwards. So although we're finding them where it's too cold for standard liquid water, that doesn't mean that the case is hopeless for the biosignatures. I think I have a couple of slides left. We're not saying this is a sign of extant life, like by exoplanet standards. Maybe we've passed that gold standard test. We have pretty good data to biosignature type molecules. But other ideas come up all the time. So for example, one of the recent ones is that these cloud sludges are broken down in some ways, and you're just getting fragments of more complex molecules, but you don't need that to be life. We really need particularly lab data before we can say how much of this stuff is there and at what height in the atmosphere is it being made? Is it being made in the nice warm clouds? We need to go back to the telescopes and do a bit more. I'm really pleased this project, Opticon RadioNet, have awarded us time just now to check out, see if we can recover an ammonia spectrum at the Sardinia Radio Telescope, which was also shown to you this morning. Okay. So, wow, now it won't change slide. There we go. Yes, that's running, amazing. Trying to do a few non-astronomer things just for variety. A very talented master's student working with me last summer, Ben Fry, has made his code available to you. He wrote a cellular automata code to see if you could have microbes thriving in droplets in a Venusian-like setup. So would they all die, or would they overfill their droplet and have no space left to move? And his simulations show very nicely. It seems they could keep going for generations under simple rules. Okay. And then finally, we had some chat about, single-celled organisms, a little bit boring. Let's see, maybe they could be bigger things. So this is where your audience participation comes in. I did show you a picture at the beginning of a terrestrial airborne microbe. And we were a little thinking about what's the best kind of thing to fly? What is the best shape? So this is what you have to do. I'm going to need some people near the front to put their hands up in a moment. We have models. Okay. Based on this genuine research paper, my severe apologies to them. These are bigger and slightly more colorful. Your job, if you catch one, is to throw it behind you to another person and so on and see which is the best shape to fly to the back of the room. Please, if you're sitting near a camera or a screen, please be a little bit careful. Okay, who's got their hands up? Chris, of course you do. Whoa. I think, anyone else? I have 7 of these. This side of the room. Okay. You get the TARDIS one. I don't know what that is. There you go. Okay. We're going. Okay. If you get it to the back. Oh my God, this is actually working. If you get it to the back, please hold it up so we know the winner.
Yeah, right.
And also you get to keep it, so thank you very much.